everyone. In this session, we are going to discuss about modeling of mechanical rotation system. So, what is modeling? Normally, modeling is nothing but we are converting the physical parameters into a mathematical parameters in order for the analyzing purpose. So, the mechanical system for control system, we have two types of mechanical system. One is translation system, the other one is rotation system. So, translation system is nothing but the objects which move in a straight line. Okay, and next comes the rotation system. This is the systems we are going to discuss in this session. So rotation system is a system which rotates in a fixed axis. So that is, we call it as a rotational mechanical system. It rotates in a fixed axis. So when an object rotates in a fixed axis, we will call it as a rotational system. And here we have in translation system also we have three basic elements, and here also we have three basic elements: moment of inertia, torsional spring, and dashpot. Okay, so these are the three main components we are going to deal. And in translation system, uh, our component we have deal with force. Okay, and in rotational system also we are going to deal with force of moment of inertia. But since here you're dealing with rotational system, so the rotational force we'll call it as obviously torque, right? So here we are going to deal with torque. So opposing torque and applied torque, we are going to deal with these things. And in translation system, it's in the force in the straight. I mean, the object moving in a straight line, there will not be any rotational forces. So there will be a dealt about force and the moment of inertia. Normally, what is moment of inertia? For example, if I'm giving force to an object, it's suddenly there is an opposing force, right? That one we'll call it as moment of inertia. So if a torque is applied on a body, then there will be opposing force, right? So that one, it's due to the moment of inertia. So here the opposing force, right? Here, the opposing force will be directly proportional to the acceleration of a body. Okay. The opposing torque, sorry, the opposing torque is directly proportional to the acceleration. Okay. So how we can, when I'm removing this proportionality sign, I have to replace with a constant. So that constant is J. Okay. That is moment of inertia constant. And the acceleration is nothing but rate of change of angle, right? So that is the thing here we have done. So the moment of inertia can be written as J into d square theta by dt square. Okay. Next comes the torsional spring. The torsional spring is nothing but it's a rotating spring, right? Okay. The torsional spring, if a torque is applied, so there will be opposing force, right? When I'm applying a torque, normally there will be the opposing torque of that object, particular object. Here in torsional spring, is the opposing torque is due to elasticity. When I'm pulling it, there will be an elasticity. The torque depends on the opposing torque depends on the displacement. That is how much I'm pulling this string. Okay, so here the torque, right? The torsional torque is directly proportional to the angular displacement. So normal displacement, since it's rotating, we'll call it as an angular displacement. Okay. So when I'm removing the proportionality sign, I'll be replacing it as K constant. So next comes the dashpot. Okay. So here, when I'm applying a opposing torque, there will be an opposing, when I'm applying a torque, there will be opposing torque. It is due to the rotational friction of the dashpot. Okay. So this torque, this opposing torque is directly proportional to the angular velocity. So angular velocity is nothing but rate of change of angular displacement. So now the opposing torque is directly proportional to the angular velocity. So I'm removing the proportionality constant. I'm replacing it as B. So B and angular velocity, I can write it as rate of change of displacement. So that's all with this opposing torque of dashpot. Now we'll come with the problem. Consider the following system and determine the transfer function. So what does mean by transfer function here is a transfer function is nothing but ratio of Laplace transform of output divided by Laplace transform of input. So yeah, here you have to find the Laplace transform of output by input. It's nothing but output by input, but in terms of Laplace transform. Okay. So before that, we have to we have to convert this physical system into a math parameter. So these are your physical system. We have two moment of inertia J1, J2, and we are going to converting it here. So first thing you have to do is you have to draw the free body diagram for two moment of inertia J1 and J2. And what are the components connected in J1? Here we have T, here we have T1, K, B12. Okay. So T is nothing but applied torque. So the applied torque will be in this direction. Okay. And the opposing torque, right? It will be in the opposite direction. Keep in mind, it will be in the opposite direction. So this is TJ1 and the torque for moment of inertia, torque for spring and torque for dashboard, opposing torques. Okay. So here we have three components connected K, P12. So TJ1, TB2 and TK. And now we have to calculate the opposing force of these three components. As we have previously discussed, so what is the opposing torque for moment of inertia? It's Tj1 is equal to, here we have how they have denoted in this problem, and we are going to take the same parameters. So J1, what is the angular displacement? Theta 1 divided by dt square. And for opposing force for B12. See here, this B12 is connected between these two displacements. So keep that in your mind. B12 is equal to T by D by dt. And the difference between these two displacements, theta 1 minus theta. And K is also connected between J1 and J2. So K into theta 1 minus theta 2. So according to Newton's second law, sum of applied torques is equal to sum of opposing torques. Sum it up and you'll get the answer like this. And take Laplace transform on both sides. So J1 into S square theta 1 S plus J into B12 theta 1 of S minus theta S. So solve it and take theta 1 as common. So that's all with this moment of inertia of J1. And now we have J2, right? So draw the free body diagram for J2. We don't have any applied torque here. So theta and the opposing torque of all components connected to J2. Solve as we have solved previously and solve it, and next simplify this and you'll get the answer. Final output by input, that is your transfer function. So here is a question: which of the following represents the rotational equivalent of mass in translational systems? Force, torque, moment of inertia, angular velocity. Which represents rotational equivalent of mass? It's and moment of inertia. So that's all with this session. Thank you.